Good morning, everyone. Welcome to today's seminar. I am pleased to introduce our speaker, Fabio Rigamonti, first year postdoc working at INAF Observatory in Brera. Fabio got his PhD in 2024 at the University of Insubria, working on the decomposition of galaxies through dynamical modeling with applications to large samples. And in the meantime, he started working also on the detection and characterization of massive black hole binary candidates through the analysis of the spectral and time domain properties. Before giving the floor to Fabio, I would like to remind that you will have the opportunity to ask questions and make comments at the end of the talk. Those joining remotely can write their questions in the chat or raise their hand to ask them directly to Fabio at the end of the talk. And now I'll lend it over to Fabio for his talk, kinematic budgets and this implication for galaxy evolution. Thank you.
Okay. Thank you very much for the presentation, for the introduction. So today I'm gonna tell you about disks and bulges, or more in general, the structure that you can observe in local galaxies, and what can you learn from them by studying them in the context of galaxy evolution. So this is basically most the work that I did during my PhD thesis, but it's still a line of research that I'm pursuing right now. So very briefly, in this talk, I will start by giving you an overview of what galactic structure are, in particular bulges and disks, and especially in the context of the so-called two-phase formation scenario. And then I will define some nomenclature to clarify the different kind of bulges and disks. It is a bit funny that before I will introduce them and then I will define the nomenclature, and this is already telling you that we have.
Allora, okay. Un attimo, ho messo queste qua perché televisare che stavo fuori. Mettile davanti lì nella cosa, va bene? Aprila e un po' la macchina, dai.
Mi senti? Yeah. Can you hear? Okay. 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 So as I was saying, I will before introduce bulges and disks, and then explain some of their properties, and then define the nomenclature. And this already tells you that we have some controversy in the literature. And as we will see, this is going to be somehow a problem in the interpretation of the results. Then I will introduce you our approach to the bulge and disk decomposition. And finally, I will tell you about the results that we got by applying this new methodology to the largest sample with integral field spectroscopy, which is MANGA. So let me start from the first principle. This is the Hubble tuning fork. I guess everyone is familiar with it. But besides being a simple classification scheme for galaxy, it is still difficult to be fully understood. And the reason for that is because it includes a number of correlation and dichotomies between different galaxy properties. For instance, it divides between elliptical galaxies, which are supposed to be roundish or spherical objects dominated by random motion of the stars, against disk galaxies. But among these galaxies, it divides between those with still star formation or those without star formation. And similarly, at fixed stellar mass, you can see galaxy with more prominent central spheroid and less prominent central spheroid. This number of bimodalities or correlation well fit the classic or a simplified picture of the evolutionary framework in which galaxy evolved in two phases. A first phase happening at early times, which is dominated by a violent evolution involving merger or rapid gas collapse and shocks. And this is supposed to be associated with the formation of bulges and elliptical, or more in general, with dispersion-supported structure. And with dispersion support, I mean structure which are dominated by random motion of the stars. On the opposite side, at later stage, the evolution is dominated by a quiet phase in which galaxy evolves secularly, forming disk and creating star in situ in ordered motion. Okay. So the point is, by looking at the presence of those kind of structure in local galaxies, since we believe that those structures are formed by different processes, we can study the past evolution of the galaxy, answering somehow the fundamental question whether galaxies are mostly made by merger, or how important is gas accretion and local star formation. The way this has been done is purely from a photometric approach, in the sense that you observe for local galaxies the surface brightness, the image of your galaxy, and you try to model it with a number of components, typically two, one associated with the bulge, which is the central concentrated structure, and one associated with the outer disk. So let me already stress that this comes purely from the image, so there is no guarantee that the structure that you identify is actually dispersion supported in terms of kinematic or rotational support. Okay. Once you do this exercise for a volume complete sample for a large number of galaxies, and you do that as a function of total galaxy stellar mass, and today we are going to focus on the high mass range, you pretty much realize that below 10 to the 11th solar masses, disks and spheroids or bulges nearly equally contribute to the mass budget. Okay. As I go up in mass, the contribution from spheroidal structure or elliptical galaxies become more and more important and dominates. Let me anticipate that these results is dependent on visual morphology. And what I mean? It means that I look at the galaxy. If I say that this galaxy from visual morphology is an elliptical, that I already assuming to fit it with a single profile, and therefore to associate all the mass in the spheroidal component. Okay. We'll come back to this plot later on. Nowadays, we are a bit more lucky because we have integral field spectroscopy. Integral field spectroscopy allows you to measure at each spatial position of your galaxy a spectrum, okay? And from the spectrum, you can infer not only the surface brightness of your system, but also the motion, namely the ordered motion, the line of sight velocity, and the velocity dispersion. Using this information, you can now classify galaxies based on rotation, whether they are fast rotating galaxies or slow rotating. And if you do the same exercise as before, you redo the mass budget, you find a very different picture in which most of the mass is actually fast rotating system or galaxies which are dominated by ordered motion. And the contribution becomes equal to the one of slow rotators, just about 10 to the 11th solar masses. So if you compare to the two pictures among each other, they seem to depict a different universe. In the first case, the one of the kinematic, a universe in which rotation is really important, and therefore where you be tempted to say most of the evolution is driven by secular processes. In the opposite case, where you find most of the mass related in spheroidal structure, you would be tempted to say in the early stage violent evolution, it's even today important. So as you can understand, some of the different are actually related in the names. There is no guarantee, as I said to you, that what we call here spheroid are the slow rotator here and so on and so forth. And we will come back to this point later. Now, discussing about nomenclature, let me stress one key point about especially bulges. In the literature, you can find a lot of names associated to bulges. The one that we discussed in the beginning about the photometric decomposition are what we call photometric bulges. Okay, and they are simply the central light component, which is compact and in excess from an exponential disk, okay, an outer disk. Then there are two other classes of bulges, the classical one and the pseudo bulges. Classical one, ideally, you want to define them as the component of the galaxy which is originated by violent processes. And the way you actually want to identify that is basically through stellar kinematics. So you look for the central compact component, which is dispersion support. On the contrary, you also find in a lot of galaxy pseudo bulges, which instead are more disk-like and are dominated by rotation. These nowadays, thanks to high resolution observation, we actually know that they are really disks, that we call them nuclear disks, or they are the inner part of what we call bars. So one problem in the context of the two-phase formation scenario or of the interpretation of the results before is nomenclature. So we need to be careful when we treat photometric bulges automatically as classical or pseudo bulges if we don't have the kinematics. The second point is that bulge disk decomposition is an oversimplification of reality. So galaxies are far more complex than smooth systems. For instance, here you observe an outer disk or ring, an inner part, there is a bar here, which is this structure over there, and there seems to be a central structure in the center. Already this galaxy is quite more complex, far more complex than a bulge plus disk system, but the important point is that this is the region of the photometric bulge. And you would be tempted to say this is a classical bulge because the isophotic contours are circular. And so you would say, okay, it's a spherical component in the center. It's likely to be a classical bulge. But as soon as you have high resolution observation, you see that the isophotic contours are far from being singular, except from the very center. And actually, this is not a bar. This is not a classical bulge, it's a bar. And associating the photometric bulge to the classical bulge would have overestimated the mass coming from violent process in this galaxy by a factor of about 50%. So what I want to say is that by doing photometric decomposition only, you can get even a large statistical sample, some systematic that are difficult to control. Okay. Now, for this reason, since nowadays we don't have just the photometry, we have also the kinematic, we asked ourselves if we could provide a new approach to the composition of galaxy in which the density and the stellar surface brightness, as well as the velocity and the velocity dispersion are modeled all together to obtain the information about the different components. The way we did that was through the technique of dynamical modeling, in the sense that the mass density that originates through a conversion of a mass to light ratio to surface brightness is the same which originate also the stellar kinematic. So basically the two are connected by the Poisson equation. Okay. And to do that by preserving the information about the component, we assumed analytical potential density pair for each of the component and combine them to produce the kinematic of the galaxy. In particular, we typically assume the presence of a spherical bulge, two disk-like components, and a dark matter halo for all the galaxies in our sample. Now, let me stress these are parametric profiles. They typically depend on masses and scale radii, but let me stress about few parameters that are particularly relevant. So, as I said before, we observe the surface brightness, so we have to do a conversion between mass or surface density to surface brightness. In the context of dynamical modeling, this is typically done by assuming a constant mass to light ratio, which is a free parameter of your model. In this case, we assume three still constant mass to light ratio, one for each of the visible components. This actually results in a average mass to light ratio as a function of radius, which has spatial variation, basically. And this is somehow a novelty in the context of dynamical modeling. And some of the results that we find are merely dependent on this assumption. The other point is that in order to be as mass general as possible, since while introducing bulges and disk, I was telling you that the information of the kinematic is crucial and is not trivial to model, we didn't impose the disks to be rotationally supported, in the sense that we have two parameters, I'll come back to explaining them more in detail later, that regulate basically the dynamical state of the disk, whether they are dispersion or rotational support. This makes some difficulties, this increases some difficulties in the interpretation, but I'm gonna go back and explain this. So now these are all the three parameters of the model. Any kind of simple minimization algorithm would fail in determining them while fitting the data. So we opted for a Bayesian approach. In particular, we choose the nested sampling algorithm. I'm not going to enter into detail, but one of the key points is that it doesn't require a predefined number of iterations to converge. And secondly, it allows you to compare statistically different model, or in our case, model with a different number of components. So I fit a galaxy and I can say, okay, I need just one bulge plus the disk, or one bulge plus two disks. This comes with an issue, which is the computational one, because before reaching convergence, it requires, for a single galaxy, about few millions of evaluation of your model of searches in the parameter space. And to solve these issues, we parallelize the model construction on GPUs, reaching a relevant speed up. Now, to let you appreciate how the actual parameter estimation work, this is one of an example, NDC 7683, from the Khalifa survey. These are the kind of data we deal with: the surface brightness, the line of sight velocity, and the line of sight velocity dispersion. And these are the parameters as a function of iteration. So as soon as I start the movie, okay, what you see is that the nested sampling initially tries basically random models. Then a little by little, some of the parameters start to converge. And then finally, the best fit model is found. And the nested sampling allows us to characterize the full posterior distribution for all of the parameters. Okay, now this galaxy also is a good example to let you start appreciate why we need two disk components and not just one bulge and one disk. So here I'm showing the azimutally average brightness profile as a function of radius, and the velocity, the projected velocity, as a function of radius. And I fitted them with a two-component system and a three-component system. In the case of two-component, I'm not able to well fit the velocity in the center. And this is because our assumption was of the bulge to be as close as possible to a classical one. So fully dispersion supported, no rotation there, okay? The way we account, in this case, for the excess of rotation, which is evident from the data in the center, is by including an inner disk component, which is rotating. Okay. What this is telling you that this galaxy actually has non-negligible rotation in the center, so the bulge which is there is likely not to be classical, but more some sort of pseudo bulge or a bulge with a strong rotation support. Okay. Now, our intention was to have a look again from another perspective to the mass budget of galaxy. To do that, you need a large, statistically important sample, and this is given by MANGA. MANGA is the integral field spectroscopy survey of the SDSS, targeting more than 10,000 galaxies in the local universe with a mean redshift of 0.03. And from each of the galaxy, they basically collected several spectra, one at each spatial position. And from them, you can extract the information that we want, namely the stellar velocity and the stellar velocity dispersion. And what we did was to model all the 10,000 galaxies. And from them, we reviewed the mass budget of galaxy as a function of kinematic and star formation. Before doing that, let me go back to the parameter that we call the K1 and K2, which regulates the dynamics of the disks. Okay. And again, these are the two parameters that we were referring to. They can range between 0 and 1. When they are close to 1, it means that the component that they are referring to, the inner disk in this case, or the outer disk, is entirely rotationally supported in circular motion. And when they are close to 0, instead, they are dispersion supported. As you can see, for the galaxy in our sample, we cover the whole dynamical range for both of the parameters. So we have to understand what does it mean to have a disk, which in the introduction I defined as dynamically cold, so rotationally supported, which instead here is dispersion supported. I'll try to clarify that by looking at a few examples. But before doing that, let me define two other parameters. These are the luminosity and the mass-weighted kinematic. So if K1 and K2 discuss the kinematic of the internal component or the individual component of a single galaxy, K-lum and K-mass quantifying the overall dynamical support of your system, whether it is luminosity-weighted or mass-weighted. Okay. Again, here the range is between 0 and 1. Okay. And when it is 0, it means that the whole galaxy is dispersion supported, it is a spheroid. And when they are closer to 1, the galaxy is rotationally supported. The fact that the two histograms look different is just come from our assumption of the mass to light ratios not being constant throughout the galaxy. Assuming a constant mass to light ratio would have led to identical definition of K-lum and K-mass, and no difference over there. Now, the first example that I want to show is a galaxy for which all the kinematic parameters are close to 0. And here, we observe a galaxy with no clear rotation and with relevant velocity dispersion. So this is a galaxy which is a spheroid, a fully dispersion supported galaxy. You may ask ourselves, so if it is full dispersion supported, why you don't prefer a model with a single bulge component? And the reason for that comes from our assumption of the bulge. So we assumed it to be spherically symmetric, isotropic, and non-rotating. In the case I have a spheroidal galaxy, whose isopotal contours are not exactly circular, as it is in this case, our model corrects by including a disk component, which is dispersion supported. Okay. What does it mean? It means that the inner and the outer disk, in this case, are providing a correction to a spheroidal component in the galaxy. So it will be wrong to interpret them as really disk present in the galaxy or structure originated by secular processing somehow. And this is not the problem, since as I know K1 and K2 and I have them, I can always recognize when this is happening. Now, the second example is a galaxy for which the inner disk is dispersion supported and the outer disk is rotationally supported. The galaxy overall shows a clear rotational pattern, although with non-negligible dispersion in the very center. And if you look at the images, although it is not particularly clear, that the central structure, the central compass structure, is not completely spherical. And so the inner disk in this case, which is dispersion supported, is accounting for the dispersion component in the center, which cannot be modeled by a spherical bulge. Okay, so again, even in this case, the inner disk is not a disk in the galaxy.
No.
Yeah.
But how sharp is this definition when you model the inner disk and the bulge? So are these parameters somehow difficult to constrain simultaneously on this K? I mean, could you say that?
So there is a bit of degeneracy in the sense that the inner, in this case, for instance, the inner disk and the bulge are not the two component physically distinct. Okay, they are the same component, which should be interpreted all together as a non-spherical bulge or non-spherical dispersion supported central region. Okay, but as we see, this exercise is basically telling you that whatever analysis you do, you must account and always look for the kinematic either of your system or of the internal component. And as we will see in a moment, all the results that we give are done as a function of that. So you can always recognize when this is happening and you take that into account. Now, the last example is when K1 and K2 are both indicating rotational support. This again is a galaxy which is overall rotationally supported, but compared to the case of before, there is a much steeper gradient in the velocity in the central region. So if you want, this is an example close to the one that I showed at the beginning. And this is possibly indicating that the bulge that you are looking at or the inner central region has a strong rotational support. Okay. Now, let's remember that our goal was to characterize and discuss in another way the mass budget of galaxy. And we want to do that by including kinematics initially and also star formation. So let's remember that the picture we started from was the following one with some kind of strong difference between the photometric approach and the kinematic decomposition. Okay. Now, since we have the kinematic both of the individual component of the system and as well as of the overall galaxy, we can reproduce these two diagrams by including kinematics as a third axis. And this is the way we thought of doing that. So let me go through this plot step by step. So the horizontal axis is the galaxy stellar mass, while the vertical axis is the cumulative mass fraction within different threshold of the kinematic parameter of the individual components. So here we are looking at the single galaxies and we are looking at the structure inside of it. And now what we do to build the different colors is to sit in a mass bin, consider all galaxy here of 10 to the 10 solar masses, and for all those galaxies, start to include the mass of those components which is below the different threshold of kinematic. So as I go up in the plot, I'm including more and more mass which refer to rotationally supported components. Somehow this is the brother of the sister of the diagram that I showed before from the photometric decomposition with the addition of the third axis of kinematics. And we see some kind of interesting features. So there is a clear separation from dispersion supported structure and rotationally supported structure in galaxies. And this comes out naturally, it's not imposed by us because we allowed the inner and the outer disk to be either dispersion or rotationally supported. The amount of mass in structure with intermediate rotational support is not zero, it's not negligible, but it is quite small. And also, we observe again an increase in the dispersion supported mass fraction above 10 to the 11 solar masses. But compared to what we saw before, in terms of number, we never reach 100% of the mass budget in dispersion-supported galaxy. The reason for that comes from the fact that they assume a decomposition based on morphology. And it has been discovered already a few years ago that from integral field spectroscopy, many of the so-called classified elliptical galaxies actually show a non-negligible degree of rotation. And since we don't do any assumption of morphology and we are informed by the kinematic, we don't get tricked by that, basically. Now here we looked at the properties of the individual components. We can do the same exercise by looking at the properties of the overall galaxy. Okay, and this we are looking at the luminosity-weighted kinematic. And what this diagram is telling you is basically that as you go up in the plot, you are including more and more mass in fully rotationally supported system. Okay, a galaxy that you would call fully described. As you can see, if before there was a clear separation between a cold structure and a dynamically hot structure, here we have a much smoother and broader gradient. So what is happening is that there are two competing processes. So basically, at fixed stellar mass, I can have bulges and disks of similar kinematics combining in terms of luminosity in different ways to give you the overall dynamical state of the system. Or as well, what is happening is also that galaxy with the same light content in bulge and disk host bulges and disk which can have different dynamical properties. And so you increase somehow the variety or the diversity in dynamical support when you consider the galaxy overall. This can be seen easily, maybe, from comparing a purely photometrically informed bulge over total ratio. So this is the bulge over total ratio from the composition of the surface brightness of the galaxy with the kinematics. You see that there is somehow a mild correlation, but the scatter is significant. And this again is from the two competing processes that I mentioned before. And this is strongly advertising you of using any purely photometrically informed decomposition to infer something about the structure that you are actually seeing in your galaxy, because you basically cannot predict precisely the dynamics of your galaxy from the bulge over total ratio. Now, we reviewed somehow the mass budget of galaxy by including kinematic in the picture, but we want to do a step further and include star formation rate. And the way we do that is by dividing between main sequence galaxies, so galaxies which are on the star forming main sequence, and below main sequence galaxy, namely galaxies which are below it. And we repeat the exercise. So here again is the luminosity weighted mass fraction somehow, divided by galaxy on the main sequence and below the main sequence. What you observe is that there seems to be much more mass in rotationally supported system on the main sequence. Or in other terms, there seems to be a strong correlation between the dynamics of your galaxy and the properties of star formation. We would like somehow to quantify that difference between below and main sequence galaxy and main sequence galaxy. And the way we thought of doing that was by considering just galaxy at lower masses and integrate over mass and plot as a function of the different threshold. If you do that for the main sequence and you do that for below main sequence galaxy, the difference between these two lines is actually the difference that you wanted to quantitatively compute before. Okay. Now, since we do this for lower masses, we can do this also for higher masses. But most importantly, we can do the same exercise for the mass-weighted kinematic. Okay, and you see quite a different picture. Let's focus on lower masses before. So what you observe is that the difference in the luminosity weighted kinematic case, it's much larger than in the mass weighted case. And what is happening is that as galaxies move away from the star-forming main sequence, what mostly happens is that they stop star formation, and the star formation stops mostly in the disk. So the light of the disk dims, or in other terms, the bulge over total ratio increases, but not because the light of the bulge is increasing, but because the light of the disk is decreasing. Okay. The luminosity weighted kinematic, which weighs the intrinsic kinematic of your system by luminosity, keeps this somehow bias while you move away from the star forming sequence, while the mass weighted kinematic doesn't have that bias. And this is the reason why we do not observe such a large difference between disk galaxies on and below the main sequence. This is what is so-called disk fading, namely disks on the main sequence are nearly dynamically equivalent with disk below of the main sequence. The picture is different at higher masses. There we have a similar scattering in both cases. And what is happening there, we believe, it's that another process, which is quenching your system or halting, stopping star formation, is happening on similar time scale with the structural transformation of the galaxy. More likely, violent processes such as mergers are dominant in that mass range. So before leaving you my introduction, let me also say that recently I started working also on massive black hole binaries. In particular, we look through time series or by looking at the peculiar spectral feature for candidate which may or may not be really supermassive black hole binaries. And we also try to combine these two techniques all together to provide new tests for defining candidates. So these are my conclusions. So basically, we created a new approach to model set consistently the brightness properties as well as the kinematic of galaxies. And we use that to review the mass budget of galaxy. And what we found is that there is somehow a lack of correlation between the bulge and disk content of your system coming from photometry and the kinematic of and the dynamics of the galaxy. And also that when you look, and it is important to preserve the information of the spatial variation of the mass to light ratio, especially whenever you consider properties or correlation which are dependent on luminosity weighted quantities. With that, I conclude, and I am happy to take questions. Thank you.
The first one is what band means.
Bayesian modeling of galaxies.
Okay, so I mean, a few. First one, do you analyze a huge number of manga stuff? Mm-hmm. Okay. Could you tell us something about different morphologies? I mean, let me say in another word. Do you see in all these galaxies you analyzed some differences group like isolated, post-merger group, tidal or something? And in this case, can your analysis be applied to these systems?
Okay, so I didn't went into the detail, there are systems in manga which are interacting or post-merger galaxy, and we exclude them from this analysis. And the reason why we do that is because this kind of model should be in principle applied to systems which are in equilibrium, let's say. Okay, so the results that you're gonna get on system with real strong distortion and so on and so forth, in the first principle, you will not be able to model them sufficiently well, and therefore the bulge masses, disk masses that you're going to refer are going to be wrong. Yeah. And the other point is that there are no big galaxy cluster in manga. Most of the galaxy are quite well described as isolated, as far as I know.
Well, yeah. Well, there's a bunch of people interacting, but I don't know if they were in the same the same group. Okay, and I mean I have other, but then.
Can you? Thanks for the seminar. Can you come back please to the first results of the manga application, the first one that shows the velocity field?
Stop me when I get there.
Should be this one, yeah.
Okay.
I don't know if it is my impression, but it looks like that the velocity field is not isotropic in this galaxy. It seems that the zero and the low velocity components are more on the left part rather than on the right one. Is this just my impression, or
so the outer part of this galaxy is severely biased by low signal to noise?
But the central part? Okay, so
the central part, I don't think
you cannot draw conclusions from the anisotropy. Okay.
Also because the velocity dispersion over there is about 300 kilometers per second. So it means that the broadening, when you determine the velocity, is much way larger than the shift. Okay, so probably the error here on the velocity are going to be close to the other area.
Yes. So the final consideration you made is that if we, I mean, you should not trust to anything we read or study in this galaxy dynamics without using integral free spectroscopy.
This is a very strong statement.
No, I mean, you said don't try, particularly not the plot. Yeah, probably the plot, the second plot, yeah, the plot on the middle.
So the point maybe is that if you blindly apply photometric bulge and disk decomposition on large sample, okay, and you use that information to infer something about how just that information about how bulge grows, how galaxy evolve, because some masses galaxy are more bulge dominated than in other masses, then you can get some biased result because you are not including systematic errors, in the sense that still with kinematics it's sometimes difficult to recognize when a bulge is classical or a pseudo one. And so without that it's even more difficult. But I have no doubt that if you have very high resolution photometry and you are an expert of decomposing galaxy and you do that in real detail, also from photometry alone you can get the proper content of the different components of galaxy. But okay, so that is my consideration.
Basically, three components. Are there some interaction between these components? Check.
The three components, you mean the bulge, the disk, okay. Interaction in which sense? I mean, correlation between the parameters, or? No, it's just the model. It's somehow a simple analytical model which represents the density and predict the velocity.
So the structure, not neither physical.
Detached between each other somehow, they constitute the overall stellar structure of your system. And surely they are not interacting with each other, or at least it's not possible to conclude anything about that from the analysis.
There's one question online. I can read it. Well, we can ask also the person, do you want to, can you unmute yourself and ask the question directly? Otherwise, I will read it.
Sure, I can. Hi, you hear me?
Yeah.
Hi, Fabio. I'm Luca Constantin from Madrid. Thanks for the interesting talk. My question was related to formation mechanism and different properties that you show of bulges and disks. And I would like to hear your opinion about the large number of these galaxies that we are finding at high redshift that are confirmed to be kinematically rotationally supported up to redshift 6, 7, and how that reconcile with the common picture that we have that several giga-year secular processes are responsible to forming this rotation-dominated system, and how that translates to the properties of disky or classical bulges.
It's a very hard question to answer. So the fact, the results that are coming from higher redshift studies, to me indicates that we should find an evolution which is dominated by, let's say, secular evolution or disk-like formation and a quiet evolution of galaxies. The fact that we still find a lot of mass in bulges and or dispersion supported system, to me, it's also somehow effect of resolution in your data. Because what I have the impression for, and might be my biased impression, is that whenever you pick a galaxy which is disk-like and it is very close by, and you follow it up with Muse, you actually discover that somehow if there was some sort of centrally concentrated structure, almost in all the cases, it is never a dispersion supported structure. So I don't know if this answers the question, but I think that from high redshift, we are going toward the direction of a universe which is dominated by, let's say, gentle processes somehow. And in the local universe instead, sometimes we are overestimating the mass or the importance of central concentrated dispersion supported structure. This is my impression though, and I want to be careful with that. And I don't know if this answered your question.
Sure, thanks.
I have a question actually. I'm not in this field. Last time I worked on galaxy was 20 years ago during my astronomy courses. But I studied a lot because Capaccioli was my professor was Massimo Capaccioli insisted a lot on this. And I do remember the composition between disks and bulge. And also the fact that that was a very crude approximation, the idea that the bulge are extremely dispersion supported. But even at that time, I do remember a lot of articles that were saying that the bulge has some kind of rotation, but maybe it's not dominating the energy of the entire system, but there is this contribution. What I do not understand from your talk, I mean, I understand your results is very interesting, but what I don't understand in your talk is when you are modeling with different components, So you're assuming that there is a disk component, a bulge component. Are you assuming that even your bulge has this kind of rotation, or the implicit assumption that you're saying is that you're having a further component, like a disk, that is just taking account of the part that is rotating of the bulge? So my question is mostly, are those components that you're extracting really physical, or are just describing the entire system that are being not our ideas, but are triaxial systems that are dominated partially? I mean, there is a contribution from dispersion and velocity.
What you said is true in the sense that our assumption, in my specific case for the bulge, are true because we do not assume it is rotating, and the inner disk, as I said, is somehow correcting for that. If they are not physically distinct structure, I think it's still a matter of debate, but we can get more information by analyzing the stellar population. And somehow it depends on who you speak with, but you find kind of correlation between the dynamical properties and the age and metallicity of your system. So if this is telling you there are two completely different components in the galaxy or not, I'm not sure about, but at least it's telling you whenever there is a disk, the age that you can associate with it is different from that of the central part, for instance. And so for me, this is an indication maybe the formation mechanism is really different, and maybe it makes sense to still keep the information of the structure while doing any kind of dynamical photometry or analysis of your system.
So this will require additional information, or just the mass to light ratio that is fitted from your model already tells you if the disk and the bulge could be the same kind of objects that are your only, or they are different.
In principle, you can add the additional information. So from integral field spectroscopy, you get the velocity and velocity dispersion of the star, but you get the age and metallicity map of your galaxy.
Nice.
What we didn't do, we plan to do in the future, is to do the same exercise maybe by including those additional information, okay, and associate a bulge an age to the bulge, an age to the disk, a metallicity to the bulge, a metallicity to the disk, to see if you see differences. But already in the mass to light ratio, we see differences from the mass to light ratio of the outer part and the inner part. And that's already an indication, if you want, that you have an older stellar population or a younger stellar population.
So sorry,
no.
Are also the cases where the inner disk and the inner bulge has the same mass to light ratio that would tell you that maybe those are the same objects?
Yeah. It could be it's surely a good idea to check it, and it's positive. It's most likely happening.
Thank you very
When
much.
you have a lot of parameters, three parameters, it's difficult to interpret the observation. You run your model and you obtain a set of actual parameters, but you don't know if that actual set is a local minimum.
No. The approach that I follow for the parameter estimation guarantees that the maximum of the likelihood is the one. Then it's dependent on the model. Because
when
but
you
that is
have
the
a
maximum.
set of parameters, you don't know if changing something in your assumption, you obtain the from a point of view of the physical interpretation of the same. It's difficult when you have a lot of parameters to interpret physically.
But you, for instance, if
object
if I assume a constant mass-to-weight ratio and I reduce the number of parameters, I get biased
Your
results.
model, how many parameters?
15-ish.
A lot.
Hey, but what would you do?
No, but the system.
Data are even
system is
more and more complex.
It's difficult to describe an offset with few parameters. Complexity is complex.
Yeah, I do agree.
And when
Sorry, if I may, I also have another simple question also, because I don't know the manga sample, but in my idea is that plot that you have here, the last one that you showed the ratio between the bulge to the disk fraction and how much support and that give you, if the manga sample is representative of the entire galaxy population, give you the probability in terms of if you're observing an object that is dominated by the bulge, maybe how many of those could be possible that so this is a thing.
Yeah, that's true. That's true. I didn't talk
This is a very
about
result if the sample is
no,
representative.
it's all the thing. It's corrected. So it's volume complete.
Okay.
All the results that I showed are
Are very local.
yeah. Okay. Very local.
Why do this is local? It should be much easier.
However, it's easy.
Questions? We have questions from the Zoom.
No, there are
audience.
no.
Thank you so much, Fabio, for your. See you in the next seminar.